Before I get into this, I need to correct the framing in that title, because "Wish It Wasn't Real" makes it sound like scientists found something threatening. They didn't. What they actually found is something considerably stranger, an explosion so far away it happened before Earth even existed, that behaved in a way nothing in 50 years of gamma-ray observation had ever prepared astronomers for. It lasted 7 hours instead of the usual few seconds, and after months of studying it with some of the most powerful telescopes on and off the planet, the scientists involved still can't fully agree on what actually caused it. This is the real story of GRB 250702b, the explosion that broke the standard rulebook for how these events are supposed to behave, and why the researchers studying it are still genuinely divided on what they're actually looking at. If you want real discoveries explained accurately instead of manufactured dread, subscribe now, because this particular mystery is still wide open. It helps to understand just how extreme gamma-ray bursts already are under completely normal circumstances, because that context makes GRB 250702b's specific deviation from the norm even more striking. Even a typical ordinary gamma-ray burst, lasting only a few seconds, releases more total energy in that brief flash than our own sun will produce over its entire 10 billion year lifetime. Gamma rays themselves sit at the extreme, highest energy end of the electromagnetic spectrum, considerably more energetic than the X-rays used in medical imaging, produced only by the most violent physical processes the universe generates: the collapse of a massive star, the collision of two neutron stars, or the kind of black hole formation event these bursts are generally associated with. A burst that continues producing that kind of extreme high energy output, not for seconds, but for 7 consecutive hours, represents an almost incomprehensible amount of sustained energy release, which is precisely why researchers studying GRB 250702b have struggled to fit it into any of the established categories built around events that are, by their very nature, expected to be almost instantaneous. Let's start with what a gamma-ray burst actually is, because understanding the normal rules is the only way to appreciate exactly how badly this specific event broke them. A gamma-ray burst is one of the most energetic types of explosions anywhere in the universe, typically produced when a massive star runs out of fuel, collapses in on itself, and forms a black hole, unleashing an intense, narrow jet of high-energy gamma radiation in the process. These bursts are famous among astronomers specifically because of how briefly they last. The vast majority are over in less than a minute, and many finish in just a few seconds. An almost instantaneous flash of extreme energy that, by the time telescopes on Earth have even finished swinging around to look at it, has usually already faded from detectability entirely. GRB 250702b did not behave that way at all. NASA's Fermi Gamma Ray Space Telescope first detected the burst on July the 2nd, and rather than fading within the usual handful of seconds, the gamma ray emission continued for at least 7 hours, nearly doubling the duration of the previous record holder for the longest burst ever recorded. Making the situation even stranger, researchers found signs of X-ray activity coming from the same location a full day before the main burst even began, suggesting that whatever was actually happening at the source had already been building for considerably longer than the visible explosion itself. If a story built on real, peer-reviewed research published in the astrophysical journal Letters instead of manufactured dread is the kind of thing you want more of, drop a like on this video right now. It genuinely helps this content reach more people who'd get value out of it. Hui Sears, a postdoctoral researcher in the Department of Physics and Astronomy at Rutgers University's School of Arts and Sciences, who has been directly involved in studying this event, described the situation in blunt, professional terms, stating plainly that this object shows extreme properties that are difficult to explain. That's not exaggerated language pulled from a press release designed to generate clicks. It's a working astrophysicist, directly involved in analyzing the actual data, describing a result that genuinely doesn't fit comfortably into any existing category researchers had available before this event occurred. Eliza Nates, an astronomer at NASA's Goddard Space Flight Center, put the significance in similarly direct terms, calling it an outburst unlike any other astronomers have seen in the past 50 years. If you found this level of genuine scientific bewilderment as fascinating as I did while researching it, drop a comment and let me know. It genuinely helps me figure out what to cover next. It's worth appreciating the sheer scale of collaboration this specific research actually required, because a result this genuinely contested doesn't come from a single research group working in isolation. The paper detailing the optical and infrared observations of this event, published in the Astrophysical Journal Letters and led by researcher Jonathan Carney, credited more than 24 contributing scientists spanning multiple universities and research institutions, reflecting the kind of large, distributed effort typically required to properly analyze an event this genuinely unprecedented. That scale of collaboration matters because it means the disagreement Sears described Different research teams reaching different conclusions from the same underlying data isn't a sign of sloppy or rushed analysis. It's the natural result of a genuinely large number of qualified experts independently examining an event so far outside prior experience that reasonable, well-trained scientists can look at the same evidence and draw different, defensible conclusions about what it actually means. It's worth understanding exactly how researchers actually managed to study an event this unusual, because no single telescope was capable of capturing the full picture on its own. Once Fermi's initial detection came in, astronomers around the world scrambled to point every available instrument at the same location, combining data from space-based and ground-based observatories to gather gamma rays, X-rays, infrared light, and radio signals simultaneously. That effort included China's Einstein probe, the National Science Foundation's Very Large Array, an instrument perhaps most widely recognized from its appearance in the film Contact, and eventually both the Hubble and James Webb Space Telescopes. Eric Burns, an astrophysicist at Louisiana State University involved in the broader observing campaign, emphasized just how essential that combined multi-instrument effort actually was, stating directly that only through the combined power of instruments on multiple spacecraft could researchers even begin to understand this specific event. Notably, the explosion itself was never visible in ordinary visible light at all, meaning every piece of this puzzle had to be assembled entirely from wavelengths of light invisible to the human eye. It's worth understanding a bit more about what a tidal disruption event actually looks like under normal circumstances, because that context helps explain exactly why distinguishing it from an extreme gamma-ray burst has proven so genuinely difficult in this specific case. When a star passes too close to a supermassive black hole, the black hole's gravity pulls unevenly on different parts of the star, stretching it apart in a process astrophysicists have nicknamed spaghettification, before the star's own material gets pulled into a swirling accretion disk and gradually consumed. That process typically unfolds over a period of weeks or months rather than seconds, releasing energy steadily as material spirals inward. A genuinely different physical mechanism than the sudden violent collapse responsible for a typical gamma-ray burst. On the surface, that longer, more gradual timescale might seem like an obvious match for GRB 250702b's own unusually extended 7-hour duration. But 7 hours is still dramatically shorter than the weeks-long timescale typical of most confirmed tidal disruption events, which is part of why researchers have found this specific case so genuinely difficult to cleanly categorize as one type of event or the other. Here's where the mystery deepens even further, because pinning down exactly what caused this explosion turned into its own genuinely difficult scientific challenge. Researchers have proposed several competing explanations, and as of the most recent published research, they still haven't settled on a single agreed-upon answer. One possibility is that GRB 250702b represents an unusually extreme, unusually long-lasting version of an ordinary gamma-ray burst, the standard massive star collapse scenario, just behaving in a way considerably more dramatic than anything previously documented. A second possibility involves something called a tidal disruption event, where a black hole thousands of times more massive than our own sun tears apart a star that wandered too close, an entirely different physical process capable of producing a similarly dramatic, if considerably rarer, burst of energy. A third, even stranger, proposed explanation suggests a smaller black hole, one only a few times the mass of our sun, may have actually merged directly with a companion star stripped down to its bare helium core, effectively consuming that star from the inside out over an extended period, rather than the sudden, singular collapse typical of an ordinary gamma-ray burst. If you found these competing explanations as genuinely puzzling as I did, drop a comment and let me know. It genuinely helps me figure out what to cover next. It's also worth understanding why an event like this connects to a completely separate, rapidly growing area of modern astrophysics, gravitational wave astronomy, even though no gravitational wave signal was specifically reported alongside this particular burst. The proposed scenario involving a small black hole merging directly with a stripped companion star belongs to the same broad category of extreme compact object interactions that instruments like LIGO and Virgo have been specifically built to detect through the ripples such mergers send through space-time itself. While GRB 250702b was identified entirely through electromagnetic radiation, gamma rays, X-rays, infrared, and radio waves, rather than through any gravitational wave detection, the specific physical scenario researchers have proposed to explain it sits squarely within the same broader category of events. Multi-messenger astronomy, the practice of studying a single cosmic event through several completely different types of signals simultaneously, has been specifically designed to investigate. That connection reflects just how interconnected different branches of modern astrophysics have become. With a single, genuinely strange gamma-ray event, potentially offering insight relevant to entirely separate fields of research studying the same broad category of extreme, compact objects from different observational angles entirely. NASA itself released an animation illustrating one specific version of that black hole merger scenario, depicting a black hole roughly 3 times the mass of our Sun, with an event horizon just 11 miles wide, gradually orbiting closer to and eventually merging with a companion star. That's an almost unimaginably compact extreme object, an event horizon smaller than most cities here on Earth, packing in 3 times the mass of our entire Sun, and the specific scenario NASA illustrated suggests this small but extraordinarily dense black hole may have effectively devoured its companion star from within over an extended period, producing exactly the kind of prolonged, unusual energy output researchers actually observed. It's worth understanding why researchers turned specifically to Webb, months after the initial explosion had already faded, to help settle this question. Sears led a follow-up observation campaign using Webb's near-infrared camera specifically to study the host galaxy where this explosion actually occurred, hoping that a detailed look at the surrounding environment might help distinguish between the competing explanations. What Webb actually revealed was a single, extremely large galaxy containing a dark lane of dust, a structure so pronounced that earlier, lower resolution images had made it look like 2 separate galaxies merging together, or a single galaxy split cleanly in 2 by that same dust lane. Webb's own observations confirm this galaxy sits roughly 8 billion light years from Earth, meaning the explosion itself actually occurred long before our own planet had even formed. That detailed look at the host galaxy's structure has genuinely helped narrow down the possibilities, even without fully resolving the mystery. According to Sears, the detailed picture Webb captured supports the idea that GRB 250702b was more likely a genuine gamma-ray burst rather than a tidal disruption event, based on the specific structure and complexity of the surrounding galaxy. But that conclusion remains provisional rather than definitive. Sears was direct about the genuine ongoing uncertainty still surrounding this event, noting that astronomers have only observed a small handful of tidal disruption events of this specific type before, meaning nobody yet has a fully reliable sense of exactly how such an event is actually supposed to evolve over time, making it genuinely difficult to rule the possibility out with complete confidence. She also acknowledged directly that different research teams studying the same underlying data have reached different, sometimes outright contradictory conclusions, a genuine reflection of just how early researchers still are in properly understanding what actually happened. There's also a lingering unresolved question about whether anything is actually still visible at the explosion's original location at all. Sears described the host galaxy's own structure as complex enough that it remains genuinely unclear whether any remaining trace of the original explosion can still be distinguished from the surrounding galactic material, and if any faint signal does remain, it's extremely weak, sitting right at the edge of what even Webb's sensitive instruments can reliably detect. It's worth being honest about exactly where this leaves the scientific community right now, because that honesty is precisely what makes this story worth telling accurately rather than dramatically. This is not a solved mystery with researchers simply waiting to announce a tidy final conclusion. It's a genuinely open, actively contested scientific question, with multiple credible research teams working from the same underlying data and arriving at different interpretations. That kind of unresolved disagreement isn't a failure of the scientific process. It's exactly what real, honest science looks like when it's confronting something genuinely unprecedented. A combination of duration, energy output, and behavior that simply doesn't match any single, previously established category cleanly. Sears herself struck a notably optimistic, rather than alarmed tone when discussing the broader significance of the event, describing it as a genuinely rare and significant opportunity to study the extremes of how stars and black holes actually evolve, and suggesting a GRB 250702b could ultimately turn out to be the discovery of something entirely new and previously unrecognized in astrophysics. That framing matters because it reflects how the actual scientists involved feel about this discovery, not dread or alarm, but genuine scientific excitement at having stumbled onto something that doesn't fit neatly into any existing box. Precisely the kind of anomaly that tends to drive real advances in understanding once researchers eventually figure out exactly what they're looking at. It's worth placing this specific event within the broader context of what Webb has been contributing to gamma-ray burst research more generally, because GRB 250702b isn't an isolated curiosity sitting apart from the rest of the telescope's ongoing work. Just months earlier, in December of 2025, Webb helped confirm the most distant supernova ever detected, an explosion that occurred when the universe itself was less than 1 billion years old, first flagged by its own accompanying gamma-ray burst before Webb's detailed follow-up observations confirmed exactly what astronomers were looking at. Together, these results reflect a genuinely active, ongoing area of research where Webb's specific combination of sensitivity and infrared capability keeps allowing astronomers to study extreme, high-energy events across the universe's history in a level of detail simply unavailable before this specific telescope became operational. It's worth remembering, too, just how much this specific event actually depended on pure observational luck alongside genuine scientific skill. Fermi's initial detection triggered an immediate, coordinated scramble across observatories worldwide precisely because gamma-ray bursts are normally so fleeting that missing the earliest observing window can mean missing the event entirely. GRB 250702b's unusually long duration actually worked in researchers' favor in that specific sense, giving telescopes considerably more time to lock onto the source and begin gathering data than a typical few-second burst would have allowed. That's a genuinely rare silver lining buried inside an otherwise deeply confusing event. The same extended duration that made this burst so difficult to categorize also gave astronomers an unusually generous window to actually study it in detail, across wavelengths and instruments that a more typical, briefer burst would never have allowed enough time to properly coordinate. So, what does all of this actually add up to? In July of 2025, an explosion called GRB 250702b lit up gamma-ray detectors around the world, and then refused to fade the way every previous gamma-ray burst on record had, continuing for at least 7 hours instead of the usual few seconds, preceded by a full day of unexplained X-ray activity at the same location. Astronomers combined data from telescopes spanning gamma rays, X-rays, infrared, and radio waves, including detailed follow-up observations from the James Webb Space Telescope examining the burst's host galaxy roughly 8 billion light-years away. And while that combined effort has helped narrow down the most likely explanation, a genuine, our unusually extreme gamma-ray burst, rather than a tidal disruption event, researchers still haven't reached a fully settled, unanimous conclusion. There's a genuine takeaway worth sitting with here, one that says something meaningful about how honest science communication is actually supposed to work. A headline promising something scientists wish wasn't real implies a kind of dread that simply doesn't match how the actual researchers involved have talked about this discovery. Sears, Nates, and Burns all described the event using language closer to fascination than fear, a genuine career-defining opportunity to study physics at the absolute edge of what current theory can explain. That's precisely the emotional register real scientific discovery actually tends to produce: curiosity and excitement in the face of genuine uncertainty, rather than the kind of manufactured dread a clickbait headline might prefer to imply. If stories like this, grounded entirely in real, published research instead of manufactured dread, are what you come here for, subscribe to this channel and turn on notifications, because researchers are still actively analyzing this exact event, and there's a very real chance the final explanation turns out to be even stranger than anything covered here. Thanks for watching, and I'll see you in the next one.